Welcome to the lectures on section 1.2. The notes covering this section are on pages 21 through 23 of the accompanying notes PDF. So in the last section we graphed a couple of lines. We're going to talk now about the features of lines, particularly their slope and their vertical intercepts. So if we are given the graph of a line, and we'll use a nice simple one. Let's say it has an x-intercept at 3, 0, and it has a y-intercept at 0, negative 2. The way that we determine how dramatic this line's rise or fall is by comparing how far it rises over how far it runs. So in this space of 3 units, how far does our function, or does our graph rise? Well, from this y-intercept, it rises 2, and it runs 3. So we would say that our slope is 2 over 3. Now, if I started from the upper right-hand point, I could say that my line falls 2 and runs negative 3. So I could say negative 2 over negative 3, but those are exactly the same thing. So it honestly does not matter which direction you choose to look along the line when determining slope. Now you want to be careful if we were using a formula. For instance, if I used the formula y2 minus y1 over x2 minus x1. So if I use this formula, I would need the points listed in as ordered pairs. So I've got maybe my first point could be that x-intercept, 3, 0. And that second point, the y-intercept, 0, negative 2. Alright. Now it doesn't matter which one of these is your first point or your second point, you just have to pick one and stick to it. So if this is x1 and y1, and this is x2 and y2, then we plug everything in. So I would say y2, negative 2, minus y1, 0. Over x2, 0, minus x1, 3. And that gives me negative 2 over negative 3, which is, again, 2/3. So that is the slope of that line, and that slope will remain constant, right? If I look at other points along the line, the amount of rise per run is going to stay the same, even if the points were closer together or further apart. So between the y-intercept and the x-intercept, it rises per run by the same ratio as it would between any other 2 points. Interested in returning? Now, if we were interested in returning to the line that we graphed at the end of the last section, let's find its slope. Okay, now there are a few ways we could do this. We already have a graph of this line, so we could just look at the rise over the run between any 2 points on that line. But I'm going to choose 2 points in particular. We went to all the trouble of finding the x and y intercepts. So we have the first point, let's say that's the x-intercept, which was 12, 0. And a second point, which is the y-intercept of 0, 4. So we can use this slope formula again and say the slope of this line is going to be, now again it doesn't matter which is your first point and your second point, so I'll just go in order. I'll say this is x1, y1, x2, y2. So our slope is going to be y2, 4, minus y1, 0, over x2, 0, minus x1, 12. So if I simplify that down a little, I get 4 over negative 12. I can bring the negative out front, and a 4 will cancel with the 4 and the 12, and I'll just get 1/3. Now that should look familiar. Remember the version of that line that we put in the calculator looked like y equals negative 1/3 x plus 4. And that's not a coincidence. That 1/3 is the slope. So you'll recognize this form here. In the notes we talk a bit about that. If you refer to definition 1.5 on page 23, this is our slope-intercept form. So here we have our slope, and in fact here we have our y-intercept. Our vertical intercept in this case, b. Now b is the y-coordinate, obviously, of the y-intercept. So this would tell us that our y-intercept is located at 0, 4. So, with that slope-intercept form, we could graph this line a little bit more quickly than we could finding the intercepts, both intercepts, and then connecting them up. It's really a matter of taste how you want to approach graphing these. Now, as mentioned in the notes, with a lot of applications, the slope of a line corresponds to a very tangible and interesting feature of the situation in question. So we call that the rate of change. So in the case of a line or a linear equation, for instance, if I say the dollar amount, the dollar value of a car, let's call that value, or label it as y, over time, where x represents time, presumably from the date of purchase of the car, is given by the linear equation y equals negative 730x plus 24,000. Now we can see that this equation is in slope-intercept form. We have y equals a number times x plus another number. So this would be my m, and this would be b in that standard form. So I can tell right away that the slope of this line, if this line didn't mean anything, if it were just an equation that I were interested in, its slope would be negative 730. Now, as a rate of change, what that means is for every increase in x, so for every additional month or year, or whatever x represents, this car is losing $730 worth of value. Now our vertical intercept is going to be located at 0, 24,000. And what that means is that when time begins, when we first start looking at this situation, the y value, the car's value, is going to be $24,000. So if we were interested in graphing this, we might plug it into our calculator. It's already in this form that we can use. So if I go again to the y equals screen, and I type in negative, remember be careful with your negatives, 730x plus 24,000. And we can see the little hourglass indicating that this is graphing is now gone. But I don't see anything. Now the reason for that, if we look at our y-intercept, it's at 24,000. So that's pretty large. That's definitely outside of the window that I can see. So if we were interested in graphing this, we might plug it into our calculator. It's already in this form that we can use. So if I go again to the y equals screen, and I type in negative, remember be careful with your negatives, 730x plus 24,000. And we can see the little hourglass indicating that this is graphing is now gone. But I don't see anything. Now the reason for that, if we look at our y-intercept, it's at 24,000. So that's pretty large. That's definitely outside of the window that I can see. And that tips me off that this graph, the whole line that I would like to see, never passes through my current window. So there are a few ways of dealing with this. You can do some algebra and figure out where its y-intercept is, and then manipulate your window as necessary to be able to see as much of the graph as you would like. You can also always try zooming to fit. So if you hit the zoom menu, option 10, it's listed as 0, you can get to it by hitting 0 as a shortcut key. Zoom fit will pretty much do its best to try to show you as much of the graph as the calculator thinks you're interested in. There are various ways that it figures that out. In this case, it zooms out pretty far, and you can see what it did by going to your window. We can see at the moment mine is going from -10 to 15 with an x scale of 3. So it didn't change anything there from the last application. But my y-min is down at 13,000, and my y-max is all the way up at 31,300. So we can tell there's some very big stuff going on with the y direction. Now, you'll notice that the y-axis looks kind of strange. That's because it didn't change the y scale. There's still one tick mark for every unit. Now, between 13,000 and 31,000, there are many thousands of tick marks. So I might change that to be every, 2,000. So now every tick mark stands for a 2,000, and we can see if that looks any better. And that cleared it up a little bit, but things are still a little bit unclear. So let me go back to the window, and I wish I could see my x-intercept. Now at the moment, I can only see as far down as 13,000 vertically. So if I want to be able to see the x-axis, I need to go below 0. So if I go down to maybe -2,000. Okay, now we can see that we're going to need to look out a little bit further in order to see the x-intercept. So the way you can modify your window now, since I need to be able to see further horizontally, is I can go back in and change that x max to something a little bit bigger, maybe 30. That should probably do it. Oh, not quite. Let's go out to 35. Alright, and now we can see both the x and the y intercepts, and we can see how the value of this car is decreasing over time. Right? It's worth less and less every year. Now I would just like to look at one more example in terms of graphing using the slope-intercept form. Okay, so here we have a line in slope-intercept form. If I do a little bit of advanced work, I can tell that my slope is -8, and my y-intercept is going to be located at 0, 15. So if I set up my axes carefully, I shouldn't have too much trouble graphing this function, or this linear equation. So I need to be able to see as high as 15 along the y-axis, so I will do tick marks every 2 units. 2, 4, 6, 8, 10, 2, 4, 6. So my y-intercept is going to be right there at 15. Now the reason I chose to do tick marks every 2 units is because my slope is an even number. So at the moment, my slope is -8. Now another way to write that as a ratio would be -8/1. Now that seems a little silly to write it in this form, but what that allows me to do is view this as a rise of -8 and a run of 1. So from the point that I've already plotted, if I rise -8, so if I come down 1, 3, 5, 7, 8, and I come over 1 unit, I'll find another point on the graph of this line. And I can do it again. I can come over 1 unit, I can run 1, and I can rise down 8 units. So if I fall 1, 3, 5, 7, 8, and I run 1, that puts me right about there. So now I can connect those points all up, and I have the graph of my line. And that's how you would use slope-intercept form to very quickly arrive at the graph of your linear equation. Now, the reason for the slope-intercept form is actually kind of interesting. So the derivation is quite short, and I'd like to show it to you right now. Now, a feature of any line is that any point on the line can be related to any other point by the slope. So m, the slope, is always equal to the change in y over the change in x for any 2 points. Now, if we choose 2 points, if we let y2, or sorry, if we let x2, y2 be any arbitrary point, on the line, we'll call that point xy. That's how we generally refer to the general point on the line. And we will let x1, y1, the other part of the formula, now we'll let that be the vertical intercept. Okay, now we don't know what the vertical intercept is, we're just naming it. We're going to call it 0b. Wherever this line has a vertical intercept, this will take care of it. So the slope is then related to the arbitrary point, y and x, replacing y2 and x2, and the slope, or the intercept, 0b, is going to replace the other x and y values. So minus b and minus 0 in the denominator. Okay. So this relationship between any point on the line and the vertical intercept is defined by that line's slope. So from there, if we try to clean this equation up a little, I see y minus b over x. This 0 isn't helping anything. Now if I multiply both sides by x, I see mx on the left, and I see y minus b on the right, because these guys cancel. I'm getting it out of the denominator. And finally, if I add b to both sides, I see mx plus b equals y. So if we just flip the sign, or flip the order of that, we see that y equals mx plus b. And that'll generate any point on a line as long as we know that line's slope and its y-intercept. Finally in this section, I would like to draw your attention to page 22 of the notes, which discusses linear behavior. So some general facts about how a line's slope and its direction are related. So if your slope is positive, then your line is going to be increasing from left to right. If you have a negative slope, your line is going to be falling from left to right. Now, the larger your slope is, the steeper the line. You'll recognize that the more lines you graph. And if your slope is very small, if it's very close to zero, it's going to be very shallow and not very impressive. If you have a slope of 0, your line doesn't rise at all. So you would have a horizontal line somewhere on your xy plane. And finally, if your slope is undefined, that is, if your equation does not admit a slope, if there's no slope present, your line is going to be vertical somewhere on your xy plane. So that is all for this section. Check back for section 1.3.